So, in this lesson, we will continue with the energy and rotational motion. This is the first debate about these conditions, okay? And so, if we have rotational system, like this one, for example, we have the mass, just remember the lesson, theta and torque value is applied in here. The total energy can be defined with what? 0 to theta value, moment times dt, right? Just like the f times dx, okay? It's the analogy, f dx, okay? So, you can write the what? The I0 times W dot is equals to what? The M0 with to what? Just remember the previous example. We multiply the V times dt both sides, and so this equation is multiplied with the W dt. W is the angular frequency. I0 times dW dt is equals to the m0, it's the total moment, and then just remember that the I0 W dW is equals to what? The m dt, d theta, right? And so the one of them is the what? Is the kinetic. The other one is potential, okay? And so this is the equivalent terms, right? And so if you want to obtain the kinetic energy in here, or the rotational energy, rotational kinetic energy, and then 0 to W I W dW is equals to what? The 1 divided by I times W square is equals to what? 0 to theta m d theta, right? These are the basic form to what? To build the rotational kinetic energy in here. So, how we can analyze these terms? The example can be built with the what? Consider the problem like solve the dynamic problem, okay? So, in order to consider this problem, we need to define the what? The rotational elements in here with the I and R radius. This is the inertia of the what? This pulley, okay? And so, we can give to what? To M2 in here, and also we should give the what? The M1, and also we need to define this velocity or the position of these terms. And so in order to create the potential energy and kinetic one, we need to create the reference points, just like O, origin, right? And so we can define to what? To fixed body in here in terms of the what? This is equals to the y, and so this equals to the y0, right? And also we can define another reference point in here, just like this one. This is the x, and so x0 can be defined in here. We can put anywhere based on this information, okay? And so also we have the tension in here. Just remember the static lesson or the dynamic lesson, right? In this pulley. And so if we, first of all, we need to say that if we have no additional force in here, and then we can say that the kinetic energy plus potential energy must be equalized to the another one in order to create the dynamics, right? Because the whole potential energy must be converted to the kinetic one, or otherwise is current in this position, okay? And so this is called, just remember that, conservation of energy. Okay? So how we can define the kinetic energy plus potential energy in here? Just remember that if we have this value, and so M1 is what is driven by the translational one, which is Yağmur. Which is Yağmur. How we can define the M1 kinetic energy in here? We have the X value. This is the translational. And so we can write that the 1 divided by 2 times M1 times X square dot, right? Because we have the translational motion. And also we can define the M2. But how we can define the M2 in here? Mehmet? 1 divided by 2 times M2 times y dot square. Yes. And also, which kind of kinetic energy is included in the system? Yes, rotational. And so plus 1 divided by 2 times I times theta dot square, right? And so theta. So these are to what? Kinetic energy. What is the potential one? Potential. How we can write the potential energy? Yusuf. What? Yes, yes, it's true. Just wait. M2 times G times Y and Yusuf minus yes, because the direction of these terms, just remember that if the Y is increasing, and so this must be positive, and so if the X is what is increasing, and so this could be negative, okay, is equals to 0. And so this is what? This is kinetic energy, but this is the rotational one. And so this is the what? The potential one. Okay? So this is the first case. In the second case, we should say that what is the values of the X and Y? What is the relation, Nasser, between the Y and X? What's the relation? No, the X must be equal to the Y in this case. Otherwise, we cannot complete this task, right? And so, also, we can say that the theta is equals to the what? If we have the R value in here, and so we can derive, or we can write this theta in terms of the what? The X value in here. But how? X divided by R, right? So, if this is the case, we can collect the whole information. We can put to what? To everything in here to X or X dot instead of Y. And also theta can also be converted to X dot, and then the total equation can be given by 1 divided by 2 M1 plus M2 plus I divided by R square times X dot square plus M2 minus M1 times Gx is equals to the 0. Okay? These are the total dynamics. And then X dot can be obtained from this equation, reorganizing it. Okay? And so the X dot is equals to the what? 2 times M1 minus M2 times Gx and M1 plus M2 plus I divided by R square. Right? See? X dot is related to what? To this equation. What happens if the M1 and M2 is equal to each other? Sarah. Yes. What happened from this equation? Yes, which means that Nasser, which means that we don't have any motion in here, and so this is true, right? This is in normal case. This is the case, okay? It's the real case, and so. But just look at this. This is the collective parameters in here, and so we can define to the what to this, or we can use the energy forms in order to create the total mass or total inertia by using this methodology. Okay, and so which means that we can define another topic 3.3 equivalent mass and inertia. Right? What is the equivalent mass and inertia? We should give this sentence in here, the systems mechanical parts can be rotated or moved based on to what? Mass and inertia, right? That should be included in the system. Either we should have the mass or the inertia. Otherwise, we cannot rotate or move anything in here because we don't have any energy, right? So, just see that the key A and PA are what? Conversible. So we can collect the mass and inertia as a coefficient named Nasser, named Nasser. Yes, thank you, Nasser. Equivalent. The main idea is that if we have the many mass in the system, just like the pulley system, we can collect the whole the M1, M2, I2 into the one part because it has a rigid body, and so we can collect the whole the terms into the one. This is called the equivalent, right? Because everything are in the form of the rigid. Okay? So, how we can build this mechanism 3, 3, 1, which is equals to the mechanical drives. Suppose that, in order to understand this term, suppose that we have, for example, this is a detailed shape in here, just like this one. And so we have the some root value for this rotated elements in here. Just see. And so we have another circle in here, and also this is what? This is put with this one. This is a system, okay? We have this part in here, a circular mechanical body, and so we connect another one, and so this is between connection between the tooths of these circles, and so we can rotate it. So if this is the mechanical body, and so we can write that this has the I1, right? The inertia, and also this has the W1, and also we can apply the torque. Otherwise, this cannot be rotated, Yağmur, right? So we have D1 in here. This is the what? This is the diameter of this pulley or the circular objects, okay? And so this is the D2. And so, if this is the case, so if we have the tooths just like these ones, okay? And so, this returns just like this one. And so, if we rotate the counterclockwise, the other one is clockwise, right? So, after that, if V1 is turning in just like this one, and so we have the V2 and torque 2 could be created by using these terms, okay? This coming from the what? This is the linking and connection and what? Rigid body structure of the mechanical drives, okay? This can be used to any mechatronic system. For example, the motor with the reductor, right? Okay, and so, how we can model these terms? Firstly, we need to define the new constants in here, n. N is the ratio of between to what? Theta 1 and theta 2, right? So, if we have the different values at the D1 and D2, the one of the circular material is the what? For example, the 5 speed, the other one is the 10 or smaller one because it's the reduction ratio, right? So, this n could be defined with the what? With this one. N is equals to theta 1 and theta 2. And also, this is W1 and W2, right? Because this is a rigid body shape, right? This is the ratio. And so, how we can calculate this ratio? N can be calculated with what? D2 divided by D1. Or N2 divided by N1. Which means that this is diameter, or you can calculate it with what? The tooth number on this system, okay? If we have at the what? At the D1, 10 tooth, the other one is 20. Which means that if we 2 times rotate in here, this creates the what? 1 rotation, right? This is simple. So, in the system, if the everything are defined or are given in the what? In the form of the rigid body, and so we don't have any loss. If we neglect loss, the friction or the storage energy form, okay? And then we can write that the only kinetic and potential energy are included in the system because we don't lose anything in the system. We just turn or store the energy on this one, okay? But how we can do that? Only the potential one or the kinetic one is included in here, not the spring factor or the damping factor. Just remember the previous lessons, Sarah, okay? Okay, so if this is the case, the T1, torque 1, theta 1, which is equals to what? The potential one, must be equals to the what? Sarah? Huh? Huh? Yes, this is simple. And also, we can write torque 2 is equals to the what? The T1 times theta 1 divided by 1 theta 2 in here. Because we have the ratio here, right? Theta 1 and theta 2 is equals to what? Is equals to n. Or we can write that n T1 can be written in here. Because if we know the torque 1, and so we can easily say that torque 2 is equals to this one. Because we have a linkage in here, right? So, how we can prove that the equivalent inertia in here, equivalent inertia is to what? The kinetic energy form is equals to what? The 1 divided by 2 I1 times W1 plus 1 divided by 2 I2 times W2 square. Because we have 2 objects, I1 and I2 in this shape, right? See? I1 and I2, right? And so, If this is the case, we have two rotational energy, W2, W1, sourced this energy, and so we can easily write this notation because we have no translational motion in here. So, if this is the case, and so if we have the ratio between the theta 1 and theta 2, and then we can write this equation I1 W1 square plus 1 divided by I2 times W1 divided by N square can be written in here. It's just simple math. We reorganize the equation between with the what? W1 and W2, right? Okay. And so, how we can do that? The kinetic energy in this form, if we collect the whole the W1 terms in here, just like this one, and so 1 divided by 2, I1 plus 1 divided by N square times I2 times W1 square. This is the total kinetic energy for a given mechanical system. And so, if we have only one variable, W1 in here, and so this term is equal to the what? IE, or equivalent inertia. See? This is the definition of the equivalent inertia in this system, guys. Okay? Any question? Any question? Hajar, do you understand anything what I'm saying in here? Okay? That's all? That's good, Mehmet? Okay. And so, if we have the rigid motion, and so if we don't have any spring factor or the damping ratio in here, we can convert to what? To hold I1, I2, M1, M2 into the one parameters, because we have only one kinetic energy in here. The other ones can be derived from the what? From the another one. Just like C1. We can model this system based on the what? Only using the W1, angular velocity of the one. The other one is always can be calculated with the what? With the ratio of these terms. Sarah. This is called this is called yes, equivalent formulation. So, in the next session, in complex case, we can draw another shape in here, just like this one. So we have this one, and also we have another circular material in here, just like this one, and also can give the what? This one. Okay? So, if this is the case, and then we have the I1 value in here, and also this is the material I2 value, and also this is the material I3 value, and also this is the material I4 value, and this is the material I5 value, and I6 value, right? We have the 6 different inertia in here, guys. Okay? And so how we can calculate these terms? Also, we can write that we have, for example, L1 white value in here, and also this is the R1 parameter at the reduced values of these terms. And so, for the I2, R2, and L2 is the length of these terms, L3, L4, this is the white values of these terms, this is the L5, right? This is the L6. These are all the whites of the R materials. And also R1, R2, and R3 is the radius, R4 radius, R5 radius, and R6 radius of these materials. And so how we can calculate the kinetic energy of these terms? Hajar, just help me. How we can write the kinetic energy of these terms? Okay, and so just remember, if this is a rigid body, and then we can write that at each case I1, I2, and I3 are rigid, which means that if we have the if we have the V1 angular velocity in here, and also V1 and W1 should be included in. And so I4 W2, I5 W2 and I6 should be rotated at the speed of the what? The W2, right? W2. And so, if this is the case, Nasir, we can write that 1 divided by 2, I1 times W1 square plus 1 divided by 2, I2 times W1 square, 1 divided by I3, W1 square, right? And so, 1 divided by 2 times I4 times, right now, Nasir? Yes. 1 divided by 2, I5, W2 square plus 1 divided by I6, W2 square. Okay? This is the case. So, these are the kinetic energy form. And so we can calculate the what in here? Equivalent inertia, right? Because we can convert the what, the W2 into the W1. Okay, and so see that in order to do that, this is the R3, this is the R4, and so the N can be defined with what? R4 divided by R3. Okay, and so W2 is equals to what? The W1 divided by N by using this ratio. This is simple. Just putting the every equation and every number into these forms, guys. Okay? And so, general cylinder formula. Just remember that. Cylindrical formula can be given by with what? The Iz is equals to 1 divided by m times r square, which means that we have in here the cylindrical objects, and so we can define to the what? This is the z-axis, and so this z-axis possesses the what? To its own inertia value, just like this one, right? If you rotate this value, and so the z-axis in here, right? Sarah, right? So, if this is the case, we can apply every formula in here, just like this one. The I1 is equals to what? 1 divided by rho 1, which is equals density values of this material. Okay? And also P R1 square times L1 times R1 square. What is this formula? Huh? No. P times R1 square times L1. Huh? Volume, yes. Volume times rho 1 mass. And so R1 is the same. And so we can generate what? The I is equals to what? 1 divided by 2 I P R I times L I, right? Times R I square, right? This is the R formula, okay? And then we can write the total formula in here in the kinetic energy form. Just remember that 1 divided by 2 times I1. I1 is calculated in here plus I2 plus I3. And so we can put what? The W1 square. And so I1, I2 and I3 can be concluded in here. But I4 is written with the what? Huh? Yes. 1 over n square plus 1 square I5 and 1 divided by n square times I6, which is to what? These are the complex case, but we can model it, right? These are the case, and we can use it. Just see that we have six distinct parts of the mechanical body, but we can treat everything as to what? One parameter, which we call it the equivalent inertia. And so, if this is the equivalent inertia, we can define also equivalent mass, or equivalent spring, or equivalent damping ratio, right? Right? Okay. So at the last case, we should define another example about the robot arm. So in the robot arm, we have some motor in here, just like this one. Okay, and also we have the one, and also we can build some shape in here, and we can rotate this value, just like this one. We have the motor in here, and so this motor is connected to one rod and one body, one pulley, and then this connected to the robot arm in here. But we should draw or clarify in here. Okay. So this is the motor, and also we should pull the rod, and should also give this one, and also give this one, and this is the arm. Okay, so the basic parameter or the output parameter is defined with with this theta value. We need to convert everything on this theta, because this theta is the robot arm angle. Okay, we want to control it based on this shape. And so how we can do that? We have the Im in here, and Rm, the radius values of these terms. Okay, and also this is the Ig, and also Rg1. Okay, and also this is the Ig2, and this is the Rg2, the parameter, and this is the arm. Okay, Wa, and this is the A. Okay, so how we can solve or define this equation in here? First of all, we need to write that no friction and losses here, which means that we can use the n is equals to, for example, is equals to 2, but which parameter? Rg2, Rg1, right? Rg2 divided by Rg1 is equals to the 2. We assume that, okay? Assume that, this parameter. And so, how we can write the dynamic equation in here? Just like the previous one. First of all, the kinetic energy can be given by 1 divided by Im plus Ig1 at the same speed value, right? Im plus Ig1 times Wm square, right? And also 1 divided by 2, we have two value, Ia plus Ig2, right? Should be given in here. This is the arm inertia, this is the G2 times Wa square, right? Right? And also we need to give the one more parameter in here. This is the robot arm, right? And so the shape of it is the quite unorthodox, right? Just weird. And so we can consider that this arm can be collected as the mass particle in here, just like this one. We can consider it just like the pendulum one, right? And so we can say that, for example, this is equals to what? It's the LA, and LA can be defined by using these terms. And so the center of gravity can be built with this one. This is the M. The center of gravity collects the particles in here, particle mass, and then 1 divided by ml times L WA square can be given in here, just like this one. This is the LA. LA. Okay. So the Ig1, Ig2 can be built with with the same formula. at the previous example, okay? Because this is the circular shapes, right? So, the total kinetic energy, the 1, is equals to the what? Key A. It's equals to 1 divided by Im plus Ig1, okay? Times, this is equals to what? The Wm square plus 1 divided by Ia plus Ig2 times, right now, Wm divided by n square, right? Plus 1 divided by ml, robot arm. And so times L times Vm divided by, yes, square, right? This is R to what? To total equivalent of mass, right? Right? Okay. And so this is equals to what? The 1 divided by 2 Im plus Ig 1 plus 1 divided by n square Ia plus Ig2 plus ml times L square, because this is what the mass point inertia assumption. So Wm square, okay? This is equals to the what? Equivalent energy form, okay? And so if we apply the voltage value to this motor, and then we will have to what? Rotation. But how we can model these terms in here? So if we have the information about this term, this is the what? Kinetic energy form. And so if we obtain the whole kinetic energy form, the equivalent mass, we can build the dynamics of this robot system, robot arm system. So therefore we have IE times Wm dot, okay, which is equals to the given torque value to the motor minus 1 divided by n times mg L sinus theta. Where is it coming from? Huh? Huh? Yes, potential, but it's coming from to what? To this one. Just remember that. mg L sinus theta. Just like the pendulum one, right? This robot arm has a same equation form with the one with the previous one. Okay, and so if this is the case, and then we can write that this equation can be written as to what? IE times n theta dot dot, right? We can write it, right? Because if you know the Wm, and so we also know to what? Theta Yağmur, right? Because it has a rigid body. And so it's equals to what? Torque M minus 1 divided by n times mg L sinus theta. And so the theta dot dot, right, is equals to what? 1 minus 1 over IE times n square times ml. This is the L. This is the L. And so this is the robot arm length, and so times g L sinus theta plus torque M times 1 divided by IE times n. Okay? This is what? This is our dynamics for a given torque value in this robot system. And so if we put the sum torque or give the sum torque, and then we can directly calculate to the what? To the arm position, arm angle. This is a huge advantage of the what? Of using equivalent inertia or the mass. Otherwise, we should solve at each part separately from each other. Nasser, do you understand the advantage of these terms right now? See? Is it good or not? Just say it. You just approve me, please. I need that. Okay, thank you. And so the Nasser approved me, and so we will continue safely at this moment. Okay, and so this is to what? To our system dynamic equation in mechanical form. We don't care anything about, we have 5 arm or 5 body. We can collect everything into the what? Into the one term. And we can model the what? The R system based on this information. This is a huge advantage for the what? For R notation. And so, this is our example, but in the Palm book, please solve 3.19, 3.25, 3.40. Okay? And also, I will share to what a MATLAB code implementation on my YouTube channel. Okay? About this. But you need to solve these problems. This is a highly educative for your progress in the system dynamic lesson. Okay? Any question? Mehmet. Yes, but it's not the make sense or not without make sense. It's unimportant to use to what the motor or the theta, because we can convert this equation into the motor one or theta one, right? Yes. So we can easily set that, because just see that we have the Wm motor velocity. We can convert to what? Robot arm position, right? We have 2 equations in here, and we can simulate easily to these equations. For example, if you want to simulate this value, you can either simulate this value or simulate this value. This is your option, but this is a huge advantage to what? To build the mechanical system based on this equivalent inertia. We can convert to any variable to another one by using this property. Okay? Any question, Hajar? Yok mu? Okay. Sarah, can I finish the lesson? You approve me? Oh, okay, thank you. Okay.